first case we have is Nick Shay, who's talking about monitoring here in Southeast Florida. So I'm going to be really strict on time, just to prevent the stomach grumbling from taking over. You have 10 minutes, and if you want to leave a minute for questions, that would be great. You can use this if you want. Right? Is it on?
Can you hear me?
No. There you go. Okay.
Thank you. Thank you for the kind invite to Ben and the committee for inviting us to this wonderful symposium. I'd like to talk a little bit about Succour, Southeast Coastal Ocean Observing System. It's been in place for at least 10 years now. The precursor to that was Succour, that was sponsored by the Office of Naval Research. So what's peculiar about us? There's warm ribbons of high ocean heat content water that basically surround the peninsula of Florida, go all the way up the eastern seaboard as the Gulf Stream, and of course separates from Hatteras with an eddy field that's quite complex. So the Florida Current is just offshore. It's not called the Gulf Stream here. It is actually called the Florida Current. So Succour is basically a group of people that putting together measurement models, monitoring schemes, and not just for a year or two. Rather, now that we're in our 10th year, we're starting to focus more on the long-term trends that the data are starting to suggest. So there are 11 regional associations across the U.S. Succour is one of them. We go from the West Florida shelf all the way up to Cape Hatteras. So these are the members. There's roughly 45 members in Succour, and we're always looking for more members to help us in doing a long-term monitoring of understanding our oceanic and atmospheric conditions. Who are we? We're a bunch of ocean scientists that want to really begin to try to understand not just the short-term issues associated with weather and hurricanes, but what are the long-term trends in the data sets. So we acquire a lot of oceanographic and atmospheric data in the coastal regime. This is IUS. Basically, it's the counterpart to GOOS, which is the Global Ocean Observing System. So we want to provide data to help with decision-making processes. Where is it going to flood? Where's the hurricane going to hit? How strong is it going to be? What's the role of the ocean and the atmosphere in modulating the intensity? So right now we have 13 radar stations along the eastern seaboard. We have another 3 more that's going back in that were damaged by Irma. We also have a few more that are being deployed within the next year or two. So we're starting to fill the footprint with a number of HF radars. So these HF radars basically measure every 15 to 30 minutes. And you say, so what does that have to do with climate? Yeah, but do it over 10 to 20 years. You're starting to get long-term data sets to begin to understand oceanic variability in the coastal region that may affect our valuable coasts like Miami Beach. So this is a graphic. I wanted to show this with, quote, sea level rise. This is from a 16-year time series. Brian McNulty later on in the symposium will give you a much longer time series, but this time series actually represents how long we've been monitoring with the HF radar. And you can see what the trend is. It's basically about 1.1 centimeters per year in terms of the Virginia Key. This is the maximum. We also do ocean heat content from space. We've been doing that for the last 22 years. Why do we do that? For hurricane intensity, because upper ocean heat content has been shown in some instances to be really important for rapid intensity changes to major storms. We see that the isotherm depths are actually increasing in time. So if they're increasing in time, that also means that the ocean's getting warmer within the context of integrated ocean heat content relative to 26-degree isotherm. So the gray bars just show you what's happening in October, basically September, October, November, and you begin to see that a lot of heat is occurring in our footprint over that period of time. So One of the major things we do is not only do we measure, but we archive and manage the data. So this takes a lot of extra effort. Instead of just sending data to the national network, we also start archiving it, and students start looking at the details of the data, because that's where the devil resides. We also share the data with stakeholders to make sure that they understand what we're doing, so maybe they can write out bigger checks in the long run. But basically, it takes a lot of effort to sustain observations for a long period of time. That really is the take-home message. So here, what we're beginning to do with the surface velocity field from the HF radar, we're combining it with satellite-derived fields as well as mooring data, as well as glider transects. So we begin to understand the upper ocean and the heat and its relationship to the surface velocity field. The surface velocity field does affect sea level. So this is our footprint. So we've been measuring from Dania Beach all the way to North Key Largo for a long period of time. That's quite a nice footprint. We have data every 1.1 kilometers at 20-minute cycles. The additional site over here is Ocean Cay, is one of our wish lists. We want to try to get that site up and running so we actually see back across the straits. And the other issue is we're working with Homeland Security to try to get a much higher resolution HF radar just at the mouth of the Port of Miami. So what does it mean? This is one of our footprints look like. The red means the Florida current. 1.5 to 2 meter per second currents that's just jetting off of our coast. Has a big impact on the ecosystems, has a big impact on marine transportation and search and rescue. You don't want your boat to turn over out here in the Florida current, because you're going to end up pretty far north. Over here is an example of how this current meanders. It's not just a straight jet, but it meanders back and forth. It comes towards the coast, and then it meanders further off the coast. Typically, we see 3 to 30 day type of excursions in where that jet is located. So one of my students, what he did is he converted everything from geographical coordinates with the radar into a jet coordinate system. We have started to learn a lot about the jet. So this is just an example. Core speeds, typically 1.6 to 1.8 meters per second. We see a decrease in core speed September, October, November. That's about the time of the strong king tides. The width begins to increase out here in this particular time frame. Surface transports, you see, begin to decrease during a period of time where the core speeds are decreasing. So that's a decrease in the transport and decrease in the core speed, and the intensity begins, it's relatively flat. A more compelling argument is here. I just want you to look at the lower graphic. So we used data from the NOAA AOML cable site. Basically, coastal sea level is going up as the volume transport is going down. That means the velocity field is getting a little bit wider and a little bit more dispersed. So there's a relationship between sea level and the Florida current, and that's what we're looking at now. These are my closing remarks. Basically, western boundary currents are a fact of life. They surround our coastline. We have to pay attention to them. They do have an effect on the coastal sea level, and they certainly have impacts on hurricanes that might move over our coastal regime and gain intensity. Thank you.
Hey, we have a minute for question. I have a question.
Yeah.
2019, what was happening with we had extremely high sea level here. Let's see, can we go back?
Yeah.
This 2019 fall, really high sea level, what, the data, do you have data just
Yes,
not
we
been
do.
processed yet?
We haven't processed the final 2019 data set.
Okay,
And the other part of the puzzle is Irma disrupted or damaged 2 of our radar sites in 2017. We now finally have the funds to replace them, and those radars will be delivered in March.
thanks, really interesting.